This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hey, I'm Lee Bortons, and it's Wednesday, September 13th, 2023. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss a math concept each week from our soon-to-be-released curriculum for families with students in classical conversations communities. Kirsty and I spent a lot of years working on the curriculum, and we're so excited that people want to learn more, so thank you for being here. What you got for us today, Kirsty?
So we are in week 19, open shapes, and we have this beautiful picture of poppies here to talk about. So I thought I would open up our exordium by asking you, why do you think we chose poppies, these blooming poppies, as our picture for open shapes? And Lee can't answer because Lee was part of picking this. So somebody else has to tell us why they think we chose this piece of art.
Because they're open. The flowers aren't in bud form. They're open.
Yeah, lots of things aren't very mysterious that we do.
Yes, I was going to say the same thing. Watching the flower, go from closed to open, maybe. And since it's open, maybe that's why you chose the ones already open.
Yeah, absolutely. Right. So this is a peony that has blossomed and it has opened up. Right. So this idea of blossoming. So when we think of that idea of blossoming, how does that maybe inform how we think of our children and ourselves when we're thinking about mathematics?
A desire for them to blossom, right? I mean, especially those of us who don't feel like we've had a great background in education in math. I want to see my kids blossom and be better than I was at their age. And I think I've said this before, but like the 4 years we've been doing the Math Map, I have learned more about math than I ever learned when I was in school. So I'm sure there's lots of different factors, but so I know the program works because as an adult, I've learned more about math.
So Babs, you yourself are blossoming. And here's a question. What is it that takes, whether it's a flower, right? We watch a flower grow and eventually blossom, or our children growing and blossoming. What is it that gets them from seed to blossom?
Nutrition, sunshine.
And I think of nurturing kind of their whole, not just one aspect of them, but who they are as a person, nurturing them to grow.
And time. It takes time.
So when we think of our math education, right, some things we just said there, right, we want to have them in a good environment. We want to nurture them in a well-rounded way. We want to give them time, right, and also be patient and know that it takes time to get to that point of blossoming, right? I think about my flowers that over the summer, right, we got that intense heat and they just were so stressed out, right? And they needed extra water and they needed some extra care and they needed some, right, just whatever, right, some extra nutrients maybe in that time. And so when we think of our children, and we want them to get to this place where they're this beautiful flower, right, whether it's mathematics or anything else, right, that if they're showing signs of stress, how can we nurture them and undergird them and support them in that time, right? And a lot of times, go ahead.
Oh no, so one thing that I liked about it was when you guys were giving your answers is about Phil Davis with that beautiful theories caught my eye. And I made me realize, you know what, our children are beautiful theories. We don't know what they're going to become. We have expectations of what they could be. And then that Saint Ignatius just really complements that, because our world teaches us to say the opposite. You know, and he's saying, and this is what it's like to be a parent, to toil and to not ask for rest, right? So anyway, I thought the whole thing went together beautifully with children.
It really does. All right, well, I know we could talk on this for hours, so we'll go ahead and move to our next page here, where we're talking about the math map, and where we're talking about the order and the language of mathematics. And as we're changing our focus now from being 2D to 3D, I wanted to ask you to consider, right, one of the big changes going from 2D to 3D is that when I'm considering something in 2D, right, I'm outside of it. I can get outside of it, right? But when I'm thinking about 3D, I'm stuck within 3D. So how does that change? Why might that explain why so much of our mathematics is done on paper, right? And why we reduce so much of mathematics to 2D, right? What does that, think of that being within the dimension or without the dimension? How can that change our perspective and our understanding?
I think when you're in the dimension, you have difficulty sometimes you can touch and you can feel things. When it's spot on paper, it's sometimes easier to computate. Whereas, we think of, I think of my water bottle as a water bottle cylinder. And also in the real world, my water bottle is not truly a cylinder because it has a curve at the top. It has other things happening to it. Nothing is strictly mathematical in the world that I live in, yet you're asking me to do mathematical things in the world, and it just there's kind of a pushback of no.
And I think that looking at a 3D object and holding it and turning it can help us understand some math concepts, but then being able to share that with another person or to calculate on it requires that we are able to put it into an image that can be shared more easily, because we can't just maybe share that 3D thing outside of the room if we're not all in the same room. And it reminds me too, I think I learned this at Math Map, one of Lee or Kirsty or Sherry or a combination of people talking about how Jesus, had to come into our dimension for us to know him. And I think it's beautiful that not only did he show himself tactile and he was touchable and holdable and 3D with us, but there's also the 2D, the word written, that allows us to share that and to experience it in a way that we can be more relatable to it as well.
So Jill, you said lots of beautiful things, but one of the things you said was that you can turn it. Why would I need to turn something that's 3D?
Me or someone else?
Well, you. Why would I be turning something?
Well, even just looking at a 3D diagram of a cube, either you have to show it clear so that you can see the back walls of it, or you're not seeing all the 6 sides of a cube. But with to be able to look at it and measure each one and maybe build up to the steps of a formula can be helpful.
So Jill, but that's right. So there you go. There, when we're stuck inside of 3D and we're looking at 3D things, I can't see the backside. Right? I can't see through walls. There's a limit to what I can see and how far I can see, right?
Perspective.
And, right.
Yeah.
That perspective, like I'm stuck, right? I can look outside my back window and I can see trees, and I'm fairly certain I know what's behind the trees, but I don't know, right? There could be a bird on the backside. That tree could have gotten hit by lightning and been split up the backside. And I don't know looking at it from this side.
Right? That's really interesting, because as soon as you said that, I realized that's right. Give me a tissue box and I can never see one of the sides, but I think I can see all the sides at once because my brain remembers it and it doesn't change often. But now, Kirsty, that you said that, I'm wondering if the back of my laptop screen, which I think is gray, is changing into beautiful colors when I can't see it.
I know that's one of those fun things to think about, right? Like it's like our dolls coming to life at night, which may freak some people out. But so now let's think about 2D though, right? And so if I took that tissue box and I unfolded it into 2D, now can I see all of the sides at once?
Well, one side, but not the other.
This is true. But if we're just thinking about that,
truly 2D. If it was truly 2D, there wouldn't be a back and a front, right?
Right. This is true. But that it's that idea that when we represent things in 2D, I can, and I didn't put a little whiteboard thing on, so I'm going to draw on the math map here. I'm going to move you guys, right? So I can, if I took that water bottle, I could say my water bottle is made up of these shapes, right? I have a circle on the top and a circle on the bottom, and I have a rectangle. When I unroll it, right, I have a rectangle that goes all the way across. So in 2D, I can see all the parts of that water bottle at one time. Right. So math gives us this, when we think about looking at things in 2D, math gives us this ability to one, simplify, right? So Donna's going, I know in reality, right, there's this little curve on things. They're not perfect. It's not this perfect rectangle because it kind of curves at the bottom. That's going to change it somewhat. So math usually says, look, I'm going to simplify this and I'm going to model this now with a rectangle instead of whatever that sort of weird curvy edge looks like. And so it simplifies, but it also gives us a way to take things that are in 3D and express them in 2D. Even if I'm not expressing my 3D world, when I look at 2D, can I see all the sides of my 2D shapes? Is there anything that's hidden from me?
There's only 2 dimensions.
There's only 2 dimensions, right? I can see all around my circle, right? I can see all around it. There's nothing hidden. I can see what's inside as well as what's outside. I can see the circle itself, right? So I can suddenly see, right, everything in 2D. So now, right, to kind of piggyback on what Jill was saying about Jesus, now think about if you could go into 4D, right? If our 3D-ness, we can see, we have dominion over 2D, right? Because I can come outside of 2D and I can look down on it from a different perspective, from a different plane, and I can see it all. I can see the inside, the outside, the front, the back, the left, the right. I can see it all. If I could go into 4D and somehow look down on 3D, what would we see that we can't see now?
Maybe that's having the Holy Spirit.
Yeah. The unseen nature of God, the spiritual dimension, the eternal, I think. I don't know if that's in 4D, but.
Well, we're getting that glimpse, right? But what can God see when he looks down on 3D, right? So Jesus, before he limited himself, right? He was let's think of him as being infinitely dimensional, right? So he can get outside of our 3D existence, right? He can see the back of my head and the front of my head all at the same time. I don't know how that works, right? I can't conceive of that, right? But this idea of being within my dimension and then getting outside of the dimension, right? If I can get outside of that dimension, I get a whole new perspective, right? And so when we think about God looking at us going, look, I got it, people. I know things you don't know that you can't even imagine, right? That's what he says. I see things that you can't even begin to imagine, right? Like I can't imagine being able to look at me. I can't see the back of my head at the best of times. And God's going, look, I got you covered because I can see the front and the back and the inside. So just a different, so when we think of those dimensions, right, just thinking about when we can get outside, what does that help us see? And why is it, right? That may also help us understand why so much of mathematics is done on 2D, on pen and paper, because I have dominion there in a way that I don't in 3D. All right. So this week we are talking about open shapes. And notice we are in 3D. So we're going to talk specifically a little bit about what that means to be in 3D. We're calling that human space. Astronomy is right, pointing that picture to, we're not just limited to our plain existence here, but we're thinking much broader, and then human space being the dimension where we live. So our big ideas for this week. Open shapes. So here's a question for you. How do we know where we are in 3 dimensions?
Google tells me.
Say that again, Donna.
Google tells me.
So when Google gives you your location, what does Google usually tell you?
I mean, it's telling me my latitude and my longitude on the 3D sphere in which we live. So it's giving me, I mean, and I guess there probably is, I don't know what the third coordinate there would be.
Altitude.
Yeah, I guess altitude. I'm at sea level, I'm in Houston.
Yeah, if you were a pilot and you Googled your, I guess you wouldn't Google whatever apps they have, and whatever, it would show you.
They've got something. Yeah, it would be the altitude. But yeah, it's just, I mean, it's telling me my coordinates, but then it also can narrow my coordinates to say in what's more common terms, my address, because I'm at home right now. Or, it can tell me my exact location as far as street corner and how far it is to the location I want to.
The abstract numbers of GPS, though, are really hard to relate to on a human scale. 1, because they're artificial, and 2, because we're not above the planet that we're on. And so we also know where we are by street corners and cloud formations and just the things that are familiar to us.
Yeah, and so when we talk about us knowing where we are, right, a lot of times we simplify it to 2 coordinates, because we just say, well, I assume I'm on the surface of the earth. And what we've done is we've sort of said, I'm going to call that surface as this 0 point. And I'm only going to tell you my 3rd coordinate if I'm going up higher, right? I'm become very interested in altitude if I'm climbing a mountain or rock climbing, right? I want to know how high something is, make sure I have enough rope, because that would be bad if you decided to rappel. If you're a top roper and you decided to rappel from the top where you put your rope and you didn't have enough rope. Or think about that guy that was just rescued, right? He was really far down. So then we suddenly worry about this 3rd coordinate. So it's a weird thing when we talk about with our kids, this idea of location, because we oftentimes, right, again, simplify our location to a 2D idea. But it's important to remember it really is 3D, right? That my location here, right, where I'm sitting, is different to my location if I went and was the same latitude and longitude, but in my attic or in my crawl space, right? So with the same, right, GPS coordinates, I could be in like 3 different places. Right. And so helping our kids to remember that, because of that difference again between our 3D reality and 3D mathematical space. Right. So here's another question when we think about comparing our 3D reality to our 3D mathematical space is our universe finite or infinite?
Finite and growing.
Right?
Well, that is the question, isn't it?
Right. I mean, when they talk about it, they talk about edges of the universe, right? Which suggests that it's finite.
Mm-hmm.
Begs the question of what's outside of it, right? If it's finite, what's outside of it? So there's one fun question. But when we think about mathematical space, right, and this is one of the things where we have to stretch our brains a little bit, because we tend to merge this idea of astronomy space with mathematical space. But where astronomy space is finite, our mathematical space is infinite.
Kirsty, may I ask a question?
Yeah.
Would location ever involve time, like a date?
Sure.
A location? I don't know how that interacts with this dimension, though.
So I like to think, it's a great question, Amy, because I like to think of time as being this bridge between dimensions. When we're thinking about mathematical dimensions, the patterns that we usually set up are patterns that are sort of like a geometric dimension, right? I took my point and I lined all my points up and I got a line. I lined all my points up and I get a plane. I line all my planes up and now I have this infinite space. And so if I could take this infinite space and line all the infinite spaces up, right, I'd get hyperspace. I'd get something else that we don't really understand what it looks like. But that would be the progression geometrically. But we know that we can say, okay, I've got this point on my number line at time 1, and that point moves to time 2. So now I could call time sort of another dimension, or I can talk about it bring a bridge between dimensions, right? So if I have a point and another point, in order to discuss how they changed in time, I need another dimension. So if I have my 2D location or my 3D location and it moves, I'm now going to need 4 variables to talk about that, which gives us this glimpse of how mathematically that 4th dimension would work.
Okay, that helps.
So
sort of. Thank you. Yeah.
Oh, you're welcome.
Just thinking of a timeline, like you could point to, I am, and it's September 13th. That's a location, but you're right. There's all this other part of it. So yeah, that will give me a lot to think about.
So let's look at a pattern, because when we think about our dimensions and we come into the dimensions, one of the things we're going to challenge students every single time is to go back and say, okay, what's the pattern from 0D? So put your remembering caps on and let's think. 0D has how many dimensions, variables, coordinates, and measures? 0. 0. And so 1D has how many dimensions, variables, coordinates, and measures?
1.
These are really hard questions, so think deeply. 2D has how many dimensions, variables, coordinates, and measures?
2.
So does anybody notice a pattern yet that they think is going to hold for 3D?
Yes.
So how many dimensions, variables, coordinates, and measures does 3D have?
3.
3. This is the joy of math, right? Because we can look at a pattern and we can predict what's next, and then we can say, is it true? Is it true that 3D has 3 dimensions?
Yes.
Yes, right, by its very name. go ahead and look at that top right box up there, or on the left, you can see it there. Is it true that 3D has 3 variables?
Yes.
What are those 3 variables?
X, Y, and Z.
X, Y, and Z. Is it true that a point in 3D has 3 coordinates?
Yes.
Yeah, and we can
There's
look.
3 components, right?
The vectors have 3 components, but a point would have 3 coordinates. So
okay, so even though you write it as 1, you're counting the things inside that set.
Yes.
Okay.
Right. So there's my 3 coordinates that I need, right? 1 for each dimension. And then let's think about measures. This one's maybe not on here. So let's go back, and we know there's no measure in 0D. What is our measure in 1D? Length. And then in 2D, we can still measure length, but we can also measure
area.
Width.
Area.
Width.
And in 3D, I can still measure length. I can still measure area, but now what else can I measure?
Height.
Volume.
Volume. So do I have 3 measures in 3D? So one of the joys of continuing to look at these patterns, especially with our students, is that we can take something that we know and are familiar with, and if we see a pattern, right, it helps us to make that connection to something we don't know and aren't familiar with. Right. And so before today, you may not have ever thought about whether 3D had 3 variables and 3 measures, right? But we can use this pattern, and now you're going, oh, yes, I'm familiar with these words, and now I can take this pattern to see what's true. All right. And time, just to review our launch plan. So remember, new flashcards are coming. We're very excited that there will be new flashcards, because these flashcards are going to include our computation flashcards, addition and multiplication, but we're also going to include notations. So it's going to be a language flashcard, right? So we're going to be learning notations of mathematics, and then we're going to have one that sort of does both, and we're have a fractions flashcard deck. So you're going to see some things in there that relate to the notations regarding fractions, but you're also going to have the opportunity to practice some of our very common fraction equivalents, right? So one of the things that we as adults probably know, that if I know those equivalents, right, I don't have to necessarily calculate every time, and that makes things quicker. And Jana, yes, there could be hundreds of flashcards. Yes, flashcards for everything. So we're starting right now with these 2 decks. We have several more decks that are in the works, and each deck will have somewhere around 70 cards. So, and we just put that in there. There you go. In writing. So if you have a Challenge A student next year, that complex domain will be available and will be required for use in community. So we're very excited about rolling that out across the country and seeing CC across the country being able to have a common math conversation, right? So imagine those Challenge A students getting together, just like the joy of graduation, where those Challenge graduates come together and they've read the same book and they've had the same experience. Now all of our Challenge A students, no matter where they are going to be able to talk about the same math ideas each week. And then on CC Connected, we will have the digits, the naturals, and the fractions lesson pages available, and access to the Math Map Companion. So while those digits, naturals, and fractions lesson pages are just that, they're going to be the cover and the lesson pages. They won't include any of the extras. People who are curious can go on the Math Map Companion, and they can see what the rest of it looks like by looking at the complex level that will be available on the Math Map Companion for next year. If you have a student going into Challenge A next year, I just want to emphasize that the very best thing that you can do is work through the naturals that is currently available. All of our pilot families and tutors keep telling us that the very best thing you can do to prepare for Challenge A complex is to work through the naturals. All right, any questions?
I don't have a question, but I do have a comment.
Okay.
From the previous slide, when you asked us the questions about each dimension, I think it's very hospitable that you included the word dimension in with all the things that we're looking for, because we can remember, well, we're talking about 0D, so 0 dimensions, so the answer must be 0. So those kinds of things that we find throughout the math map, I think help funnel us toward those discoveries.
So this very wise lady that I know, that I work with, is always saying, don't ask a question that they don't know the answer to, right? You always don't think it's obvious. Ask questions that they can answer. And so, yes, Jill, because that wise lady is offering these lesson pages, right? We see that she is working very hard to make things hospitable in that way. All right. Okay. So here's an activity for you. Lee mentioned a tissue box. If you have a tissue box handy, go ahead and grab it. If you don't have a tissue box, you could do this with a book or any other sort of rectangular object. My tissue box fell off of my desk, so I'm going to use my TARDIS can.
It's bigger on the inside.
It is a lot bigger on the inside. All right, so go ahead and grab hold of a tissue box if you have one, or like I said, it can be anything that's sort of rectangular. Prism is its official name, so it could be a book, right? Books, even though this one is thin, right? It is still that same general shape. And choose one corner, right? So it doesn't really matter which corner I choose, but choose one corner of your solid to be your origin and just stick your finger on it. And if that's your origin, what would the coordinates be?
0, 0, 0.
0, 0, 0, right? Because I'm defining this as my starting point. So that's one way in which in mathematics, we say the origin is arbitrary, right? Means I can pick any point. But once I choose that point, everything else now is fixed, right? Now I'm moving this around. So the space that I'm defining this to be the origin in is the space which, right, extends out from here. Right. If I was to want to name locations in the room that I'm in, I probably would want to pick an origin that was somewhere in this room, created by fixed points in the room, right? So I'm only choosing the origin for the space that I'm defining here. How many axes can I trace along? Because what point do they have to go through?
Origin.
The origin. So if I look at my origin, how many edges, right, go through my origin that form my axes?
3.
3. So what did we just discover about 3D? How many axes does 3D have?
3.
3. Isn't this lovely how this works? Right. So now, how would I define a line that goes through the interior of the box? If you wanted to describe that to me using your tissue box, how could you describe that?
It does not go through the origin?
Well, it might or it might not, right? Does it have to go through my origin? It doesn't have to, right, Babs? It's a good point.
But it could be something like segment AG. Is that what you're asking us, how to go through it?
Yes.
Yes. Okay. It also could be something from the center of plane ABC that goes through plane BFG.
Right. So Lee just pointed it right. So we have to, if I want my line to go through the inside, right, the interior of my box, can it lie on any of the planes that make up a face? Right. It's got to intersect at least, well, at most really, two. Right. It's got to intersect two of my faces. So it could be like somebody shot an arrow through and it went straight through the side. It might go through the origin, but then through an opposite point. You probably can't see that, right? So there's lots of different ways, but one of the key ideas is it can't sit on any of my faces. How many?
Because of the word through, right? Is that why you're saying that? Is the word through?
So how many planes could my faces represent, right? So if I count up your faces, how many planes could I name based on those faces?
6.
6. Can I see them all at the same time if I'm holding my 3D object?
Not if it's opaque.
No, right? Maybe Donna, that's why it's bigger on the inside, because when I can't see the base, maybe it's like getting bigger. And then when I look, right, you don't see it. Right? How many, so we've got our 3 axes, right? If I wanted to name a point somewhere on my shape, whatever it is that you're holding, your tissue box, right? How could you give me directions to that point?
We would need to name some things, I think, before we could do that.
Okay, what would you want to name?
So are we naming a line?
Okay, so go ahead. So which lines would you want to name?
Well, it's just I'm thinking about, like, if we're trying to define a line, that's the question, right?
Well, I want you to just pick one particular place on your object and then tell me where it is. What would I need to know for you to tell me where it is?
We need 2 points, make a line.
Right. So I could use 2 lines if I knew what 2 lines. So that's one way I could do it.
Or 2 points.
2 points.
Well, I want 1 point. So I could use 2 lines, right? But think back to what did we start with? We started with our origin. So
and you have to have, good.
You may need to make sure I know where your origin is. And then we said we had how many axes?
3.
3 axes. And so now you want to make sure that I know the names of those axes, right?
X, y, Z.
We use like XYZ, right? We could use something else. But so I have my X, my Y, and my Z, for example. Now, if you wanted to tell me specifically where a point was, if I knew where your origin was and what your axes were, what do you tell me next to give me to one specific point on your box?
A new XYZ.
You need to give me the coordinates, the XYZ, right? So I have my origin, I have my axes. And so if you tell me how far along my X, and then how far along my Y, and then how far along my Z, you could get me to one specific point.
So I would need either inches or centimeters or something to tell you, or units of some kind.
Yes.
Okay.
Yes, Jill, in real life, you are absolutely correct. We do need to know what units we're talking about.
Or I could name the plane if it was, you know, plane A, B, C, D, E, F, G or something. I could also name the plane, right?
Yep.
Okay.
Or line segment BG.
So I could name things, right? But if I want one specific point, all I was trying to kind of use this to review that idea that we need 3 coordinates for any particular place. But those 3 coordinates are always based off of knowing where my origin is and what my axes are, right? Because those are my, that's my base. That's where I'm measuring from. And so that kind of takes us back to 1D, when we talked about 0D and 1D, right? That in 1D, we get an origin, right? And so spiritually, right, God's telling us that he wants us to be perfect. And he's giving us this direction, and he's giving us what our origin is, right? What our goal is, what the expectation is. And so he's setting that point for us, right? If we don't know where that is, right? If we don't have a fixed truth, right? If we don't have a fixed location that we're aiming for, right? You can spout whatever you want to, right? And if I don't know, right, I could sit here and tell you that in my room, I'm sitting at coordinate 5, 6, 0. And that doesn't mean anything to you if you don't know where I'm measuring from, right? And so even in 3D, we always have to know what's that origin, what is the center point. And when we're dealing with things mathematically, a lot of times it's arbitrary, right? We pick one and then everything is measured from that. In our spiritual lives, is our origin arbitrary?
Well, it turns out it is. That just doesn't mean it gives you a good one though to have, right? All kinds of people pick origins they shouldn't be picking.
So the world definitely wants to think you can pick an arbitrary origin, but we know the truth, right? Is that, right? The truth of the Christian life in that we're trying to share with everybody is that there's one fixed origin that should be where we're measuring from for all things. And so once we know where that origin is, now I can rightly align myself, right? Once I know where that origin is, you can figure out where I am.
Yes, it reminds me, Kirsty, of you can't serve 2 masters. So we can't have 2 origins. That is just an impossibility. So that's kind of a nice idea. Thank you for, yeah.
I like that, Amy. That's a great way to describe that, right? How confusing would it be if we tried to have 2 origins? That's great. All right. My little, there we go. My arrows disappeared. There we go. So next week, we will look at solid shapes. So this week we used our tissue box to help us orient ourselves to an infinite 3D space, right? And so even though we were using a solid shape, we were contemplating this infiniteness of 3D. So next week, we're going to look at some solid shapes. And that may feel more fun because these are going to be things we can pick up and turn and look at because they're nice and solid and closed. So.
Yeah, I wanted to add just the more you guys have been the loyal, faithful ones. So in week 20, the object on the back is actually a sphere, and I wanted to point out that Kirsty is absolutely right. So week 19, which should have an open shapes. And we had to pick the flowers on the front, but on the back, we put on the tissue box, knowing that we do better if we have something we can hold on to as we play these games and do these activities. And so really the point of that box is the XYZ axis, not the solid shape of it. And then it's just, we can't put every game that works on each week. So there's a little bit of fudging.
But thanks, Lee, for pointing out, because I forgot to mention that activity was from the back of the booklet. So if you haven't seen the booklets, every booklet has a game or activity on the back that can help to extend learning in everybody's homes. So that is a great feature of the Math Map. And thanks, Lee, for pointing that out because I forgot.
Yeah, it's okay. It's good. Hey, listen, answer this question before we get off. Do two imaginary numbers exist only in two dimensions? I mean, even dimensions, right?
Yes.
That's
Yes.
so weird.
Yes, there complex numbers are 2D numbers, but then there's something called quaternions, and then there's like octians or something like that. And so they're actually they may only be powers of 2 as we look at those. It might not even just be even dimensions, but powers of 2.
So 2, 4, 8, 16, 32, like that.
Yes.
That's right. So cool.
Because it's like looking at the square root of -1, the 4th root of -1, then the 8th root of, right, keep taking the square root kind of a thing. I think that's the general idea. But the math for those gets a little bit challenging. And so we don't cover that in the math map.
Yay! I had to have somewhere to quit. All right. Thanks, everyone.
Thank you.
Have a great week.
Thank you so much.
Thank you.